What if I told you that a 1.5 billion parameter language model could outperform much larger models at complex agent tasks while running entirely on your laptop? That's exactly what a new research framework called EFFGEN just demonstrated. And it's not just about making small models work as agents, it's about making them work better than the popular frameworks everyone's been using. Hey everyone, this is RZ here. I break down the latest research straight from the papers and scientific articles, so you know what's coming, what's real, what actually matters. Link to today's paper is in the description. Let's go. Large language models like GPT-4 and Cloud are incredible at acting as autonomous agents, calling tools, breaking down tasks, remembering context, but they're expensive. They require cloud APIs, and they raise privacy concerns. Small language models with 1 to 7 billion parameters, can run locally. They're fast, they're private, they're cheap, but they struggle with the same agentic task. Their context windows are smaller, their reasoning is weaker, they fail at tool calling more often. So researchers have been asking, can we design a system that lets small models act like capable agents without needing massive compute or cloud infrastructure? That's where EFFGEN comes in. It's an open source agentic framework specifically for small language models, and it just outperformed LangChain, AutoGen, and SML agents across 13 benchmarks. I'm gonna tell about them, don't worry, with models as small as 1.5 billion parameters. So how does EFFGEN works? It's built on 4 core ideas. First one, prompt optimization. Small models are sensitive to how you phrase instructions. EFFGEN compresses and restructures prompts specifically for small models, reducing prompt length by 70 to 80% while preserving the task semantics. It simplifies instructions, uses structured tool schemas, and formats everything so that the model can parse it clearly. This alone gives an 11% accuracy boost on 1.5 billion parameter models. Second one, intelligent task decomposition, complex tasks broken into subtasks. But EFFGEN doesn't just split things randomly, it supports 4 decomposition strategies. Parallel decomposition for independent subtasks that can run at the same time, sequential decomposition for tasks that depend on each other, hierarchical decomposition for a manager-worker structure, and hybrid decomposition that combines both. This means that the system can handle everything from simple queries to multi-step research tasks. Third one, complexity-based routing. Before executing a task, EFFGEN calculates a complexity score using 5 weighted factors. If the score is low, it routes the task to a single agent. If it's high, it triggers automatic decomposition into multiple agents. This pre-execution decision prevents small models from getting overwhelmed by tasks they can't handle on one shot. And interestingly, this routing helps larger models more than small ones because bigger models benefit more from strategic task splitting. Fourth, a unified memory system. EFFGEN combines 3 types of memory: short-term memory for conversation history, long-term memory that scores and stores important episodes, and vector memory for semantic retrieval using embeddings. This lets the agent remember context across long interactions without blowing up the token count. On top of all this, EFFGEN unifies 3 major agent communication protocols, MCP, A2A, and ACP, into one framework. So it's not just optimized for small models, it's also interoperable with the broader agent ecosystems. Now let's talk numbers. The researchers tested EFFGEN against 4 baselines: raw models with no frameworks, LangChain, AutoGen, and SMLog. They evaluated across 13 benchmarks covering math reasoning like GSMB8K and Math 500, algorithmic reasoning tasks, retrieval, web searching reasoning, long-term memory benchmarks, and multi-tool agent tasks like GAIA. The headline results: EFFGEN paired with QN 2.5-7b achieved 63.07% average accuracy across all benchmarks. That's a 12.3 improvement over the raw model baseline. And the gains were even more dramatic at smaller scales. At 1.5 parameter, EFFGEN improved performance by 13.1% on average. The framework also reported up to 18 times faster execution for small models, lower memory usage, better task success rates than competing frameworks. One of the most interesting findings came from the ablation studies. When researchers removed prompt optimization, small models suffered the most. But When they removed complexity routing, larger models suffered more. That suggests these two systems are complementary. Prompt optimization helps weaker models understand instructions better. Together, they create a scalable agent architecture that works across model sizes. This paper points to a much bigger shift happening in AI right now. For the past few years, the industry has been focused almost entirely on scaling models larger and larger. But EFFGEN shows that system design may matter just as much as raw model size. Instead of asking how do we build bigger models, the question becomes how do we make smaller models smarter through architecture? And that matters for several reasons. If small models can operate as a competing autonomous agents, companies can deploy private AI systems on local hardware without relying on expensive cloud infrastructure. Second, efficiency becomes a competitive advantage, and optimized 7B models running locally may become more practical than a giant frontier model that costs dramatically more to operate. And third, agent frameworks themselves are becoming the bottleneck. The paper basically argues that current frameworks were designed around large models. EFFGEN redesigned the stack specifically around constraints and smaller models. Now, there are still limitations. The framework improves performance significantly, but it doesn't magically turn tiny models into GPT-5 level systems. Complex reasoning still benefits from larger models. And the paper focused heavily on benchmark evaluation. Real-world autonomous reliability remains an open challenge across entire industry. EFFGEN is one of the clearest examples we've seen for a new AI trend, smaller models becoming dramatically more capable through smarter orchestrations. Instead of brute forcing intelligence with scale alone, this research combines prompt compression, intelligent routing, task decomposition, and layered memory. And if this trend continues, the future of AI agents may not belong exclusively to giant cloud models. It may belong to efficient systems that run privately, cheaply, and locally while still performing at a surprisingly high levels. That shift could change how AI agents get deployed everywhere. So quick breakdown. LangChain is popular Python JavaScript framework for building LLM applications, provides pre-built components, chains, sequential queries, agents, autonomous decision making, and memory modules, vector store integrations, and tool connectors. Abstracts away boilerplates but can feel heavily and opinionated. Good for rapid prototyping. AutoGen is Microsoft multi-agent framework, focuses on conversational agents that collaborates. Agents can chat with each other, delegate tasks, and solve problems through dialogue, supports human-in-a-loop workflows, designed for complex scenarios where multiple specialized agents work together. For example, a coder agent plus a reviewer agent, and SMO agents, Hugging Face, lightweight agentic framework, minimalist design, under 1,000 lines of code, built for smaller models, for local deployments, emphasizes simplicity, transparency, and efficiency. No heavy abstractions, just core agent primitives like tool callings and memory. Think of LangChain, but stripped down for resource-constrained environments.